This is a cross section of an axon showing membrane and the ion channels present in it. This is the action potential recorded at this particular site. During the depolarization phase of the action potential, positive ions enters inside the axon. And once the charges are inside, they are going to spread in all directions. And some of them reaches the neighboring voltage gated sodium channels and they are going to open them. So this is going to set up an action potential here. Again, positive ions are moving inside. This cycle repeats, that is the spreading of the charges and opening of ion channels. So that is how basically the action potential propagates in the membrane. But what is the most important factor which decides the speed of this action potential propagation? That is how far the charges spread. That is, charges once they are entering inside the axon during a depolarization, they have to spread as far as possible to open more and more voltage gated sodium channels in the distant side. So this is basically going to determine the speed at which the action potential is propagated in the axon. I'm going to use a door analogy, door opening analogy to explain this, how the charge spread is going to help in determining the action potential velocity. Assume this opening of the door as the opening of voltage gated ion channels. And once the door is open, that is the voltage gated ion channels are opened, the positive ions are going to come inside and they are going to spread. If they are spreading only for a shorter distance, that is if they are spreading till here, it is able to open only this gate at one time. And again the charges has to come from this this ion channel to move in further direction to open the next gate. So in this, if the spread of charges is small, it is going to open one gate at a time only. So it will take a long time before this the voltage gated sodium channels on the farthest sides could be opened. What if the charges coming inside can open the doors at the distant side? Something like this. So here this door, the opening causes the ions moving inside. The charges are spreading for a longer distance, causing action potential by opening of sodium channels even in the distant sides. So compared to the first case, the opening of ion channel and thereby action potential propagation is much faster in the second case. And this is basically due to the spread of the charges. Here it is, the charges could spread for only shorter distance and here for a much longer distance. There is a term called length constant which is used to describe how long the charges are going to spread. So the length constant is the distance at which the charge strength becomes 37% of the original. Higher the length constant, farther the charge travel before they are dissipating. So the action potential conduction velocity is much higher with higher length constant. The length constant of a neuron is determined by the electrical properties of the axon and mainly the membrane resistance and the axial resistance. This is the formula which relates the length constant lambda to the membrane resistance and the axial resistance. That is, lambda is equal to square root of the membrane resistance by the internal neuron resistance, also called as the axial resistance. So when the neuron membrane resistance increases, the length constant will also increase, thereby the velocity will also increase. Or if the internal neuron resistance or axial resistance, if it decreases, again the length constant will increase, thereby action potential velocity is increased. Let's see what is this terms membrane resistance and axial resistance mean and how can we improve it. First, the membrane resistance. It is the resistance offered by the membrane for the movement of ion through it, either from outside to inside or from inside to outside. So this membrane has a hydrophobic core in the center. This is going to cause a huge resistance in general. But there are ion channels present in the membrane which is going to bring down the resistance, and these are the pathways through which the ions moves inside. Otherwise, the membrane has a very high resistance. So The term specific membrane resistance is used, which is denoted by capital RM, which denotes that membrane resistance per unit surface area of the membrane. So for 1 centimeter square, how much is the membrane resistance will be. So this is actually depends only on the number of voltage gated ion channels present on the membrane. If the voltage gated channels concentration is higher, then the specific membrane resistance becomes much lower. The second property of the neuron, which is going to determine the length constant, is the axial resistance or the internal neuron resistance. It is the resistance offered by the axoplasm for the movement of ions, also called as the internal neuron resistance. So these are the two properties, that is, one is the membrane resistance and second is the internal neuron resistance, which are going to determine the length constant. And we know that higher the length constant, farther the charges travel before dissipating. So how to improve the length constant? By changing the membrane resistance and the internal neuron resistance. The internal neuron resistance can be simply decreased by increasing the axon diameter, something like this. So when axon diameter is very small, the resistance offered for the movement of ion is much higher. But if the axon diameter is much higher, it is something like adding more and more resistance in the parallel circuit, which is going to decrease the total resistance of the circuit. So here, as the diameter of the axon increases, the charges have less friction, they have more space to move easily forward, so the resistance decreases and the length constant improves. So the second property, that is the membrane resistance, it can be improved by the process called as myelination. So myelination is the process, it's done by the oligodendrocyte in the central nervous system and the Schwann cells in the peripheral nervous system. Here the multiple layers of membrane of either this oligodendrocyte or Schwann cell is wrapped around this axon. Something can be represented like this. So this is our original axon and this is the membrane on both sides of the axon. These are the extra layers which are the membrane of the cell membrane of either oligodendrocyte or the Schwann cells, which are added to our axon membrane. Actually, the membrane resistance is the resistance offered by a membrane for the movement of ion inside it. Now we have multiple layers of membrane, so the ion has to pass multiple membranes and then finally reach here. So it is something like adding more and more resistance in a in series circuit, something like this. So this is going to increase the total resistance, and the membrane resistance increases. The charges which are entering the neuron have no way to escape outside, so they go more forward. That is, the length constant of the neuron is improved by increasing the membrane resistance. And there are sites in the axonal membrane where there are no myelination. We call it as the nodes of Ranvier. These are the sites where the membrane resistance is very less because there is no myelination, and also there is high concentration of voltage gated ion channels in the nodes of Ranvier, which drops the membrane resistance. So the action potential is initiated in the nodes of Ranvier. At these nodes of Ranvier, the membrane resistance is around 20 to 50 ohms, whereas in this myelinated segment, the membrane resistance is around 10 power 9 ohms in that range. So this is how the magnitude of increase in membrane resistance due to myelination. So in summary, myelination increases the membrane resistance, thereby improves the length constant, and hence the conduction velocity is increased. Thank you.